Okay. Welcome back. So our next speaker is a new entry in this community that you joined us. It's a physicist. You got to know him a little bit. I met him 1 month ago now, so that's the second time we saw each other already. Third time. No, first time was online. Well, nobody can know. Sorry. So Daniel Sudarsky from Mexico is going to speak about the relevance of conceptual problems afflicting quantum theory for cosmology and black hole physics. Thanks, Daniel.
So, well, thank you very much. Thank you for inviting me to the community and to this very nice conference. I know I have to try to address people with various different backgrounds. So, if you have a question that is just explanatory, if there is something that I said that you don't know what it means, please stop me and I'll ask you. For questions that are more of a discussion type, I will follow the standard procedure and leave them for the discussion session. But please stop me if I say something that I don't know you guys, so I'm making a guess of what things will make sense. Okay, I should make some clarifying remarks to start. The first clarifying remark I should have made is that I hope you are all aware that we have conceptual problems in quantum theory. We are not completely satisfied with the textbook version of quantum mechanics, right? We have this, to start with, we have these two evolution laws, one when you are not looking at the system and one when you are looking at the system, and what that we don't know exactly what it means to look at the system. Anyway, that's just one of the problems, and that's what I mean by the title. Looking at those problems or ignoring those problems, I think, has relevance for actual the physical conclusions that you can get from things. The second word is about methodology, because I have, the subject that I'm going to talk about is one in which you are required to deal with both relativity and general relativity, moreover, and at the same time with quantum mechanics. Those are the problems that interest me. And normally when you think about it, you think about, string theory, loop quantum gravity, some scheme in which you start with the quantum theory of gravity. And I call this the bottom-up approach. This is the usual approach. You assume you have in your hands the fundamental theory of gravity, of quantum gravity, and you start working out to try to make contact with the world out there. That is an okay approach in the sense of it is certainly valid, but it makes a great bet about believing that you have in your hands the correct theory of quantum gravity. I'm more conservative, and I like to take a different approach, which we call the bottom-up approach, which is to take theories that we have learned to use with trust, we have good reasons to believe they contain a lot of truth, and look at the places where they collide and they don't seem to match, try to see what patches I may have to put on top of them so that they can deal with a particular situation, and hopefully learn from those patches something about what the nature of the more fundamental theory should be. Okay, so it's a very different, if you want, complementary approach to what most physicists do in this field. So for our idea would be to push general relativity together with quantum field theory, so it's the version of quantum mechanics that embodies relativity to a largest extent. And that, when you try to do that, this approach is known as semi-classical gravity, because gravity will be treated classically and quantum field theories are going to be treated quantum mechanically. And at the same time, we will try to focus on the occurrence of conceptual difficulties in this exploration. Okay, so one of the difficulties that arises in the studies is the fact that, as you know, quantum mechanics, the state of a system often tells us that the system doesn't have a well-defined value of a quantity. It only acquires a well-defined value if you force it to be an eigenstate of that corresponding operator. And then we describe the system in terms of a wave function that describes, characterizes also the level of uncertainty that we have regarding what could be the result of measuring that quantity. People refer to these things, to quantum uncertainties or quantum level of indefiniteness, as quantum fluctuations. And this is a terminology that we find very problematic, because fluctuations are used, the word fluctuations is used for often for something completely different, which are actual stochastic fluctuations, things that are changing from time to time. That could be some quantity that varies, has definite values at each time, but jumps around, like the position of a Brownian particle, or fluctuations of the level of the seed, let's say, they change in space and time, or fluctuations of grades in students in an exam, and this type of confusion is very, very problematic. It's completely unjustified, and is very problematic. These occur in various places, for instance, in our cosmological ideas. I will mention three here and two. One is the emergence of the seeds of cosmic structure during inflation, our best theory of cosmological evolution at this point. The generation of primordial gravity waves during inflation as well, and something else called the problem of eternal inflation, on which I will have almost no time to talk about. It's true that quantum uncertainties may be taken as a measure of the dispersion in the results of a measurement of a certain quantity. If you make many copies of the system and subject it to a measurement, you will obtain different results, and the spread of this result is characterized by quantum uncertainty. But there is a measurement involved there, in measurement that changes the state of the system, that does violence on the system, that injects or removes energy from the system in some way or another. My point is that treating these quantities as if they were jumping around, these quantum systems, as if they reflected some jumps around, without a situation in which you could point to a measurement, is a very serious problem, and connects, of course, to what I like to call the end problem, the measurement problem. I think is one of the main problems of theoretical physics that is not there being addressed. The first observation is that cosmology is a setting in which you cannot even point to a measuring apparatus or a measuring or an observer. You want to describe the situation, the physical situation, before observers or measuring apparatus ever came to existence. So you cannot call upon those to play any role. But it's not the only place where you get into problems. If you take, you say, oh, okay, this is philosophical nitpicking, and try to forget about it and say, okay, whenever I have uncertainty, I have a system jumping around from value to value within the level of uncertainty. You get also into problems. This is something we found just recently with certain quantity called the electric dipole moment of the neutron, which happens to have been measured with exquisite precision. So doesn't matter what it is, but look at the level of precision that people have, that our experimental colleagues have put, and the quantum uncertainties are at least 10 orders of magnitude larger. So it's completely impossible to understand how these people could have achieved such precision if you took the view that things are jumping around. Okay, let me not go there. So let me go back to the cosmological setting. Inflation is today the most accepted version of cosmology. Basically, 99.9% of the cosmologists work assuming inflation. And it refers to a very early stage of extremely rapid acceleration in the evolution of the universe, which then slow down when the process finish. Is supposed to represent growth in the scale factor of the universe, if you want, in the length size of the universe by at least 60 orders of magnitude, or increasing the distance by at least e to the 60, a factor of e to the 60, which they call it 60 n-fold. So it's a dramatic range that is meant to go from here to there. For those of you that are used to the theory, it's used to this expression. Well, please don't be scared by expressions. This is just simply to tell you what the theory is about. Here, the first part of the theory, it represents Einstein's relativity, and the second part of the theory represents the theory of a single scalar field with a potential, and that's what people use to describe inflation. These are the two elements that appear in inflation. The potential of inflation acts like a cosmological constant, and that's why you have this accelerated expansion as long as the scalar field is not changing very much. One assumes that the scalar field configuration is one which depends only on time, so it's space independent of space. And this is the story tells us that the resulting dynamics, the resulting violent expansion, basically dilutes everything that was pre-existing in the universe. The universe becomes goes into a state of vacuum for all fields and becomes extraordinarily flat, space-like flatness, and homogeneous and isotropic, and solves other issues that were bothering people. I can go into that later on. But its best success, its supposed greatest achievement, is to account for the seeds of structure that eventually evolve and produce galaxies and everything else that we see around, and in particular creates the conditions where we can exist. Okay, so let me give you a brief account of what is that story as it's normally told, and why we feel that this theoretical account is not satisfactory and that something else is needed. So the thing is very successful, but theoretically not satisfactory, and I try to explain why. Okay, as I said, the setting here is a universe that is homogeneous and isotropic, a scalar field whose value depends only on time. So everything you have is completely homogeneous and isotropic. And then you consider possible perturbations of the metric here represented by phi, which is called the Newtonian potential, and by hij, which are called the tensor modes, which are would be responsible for gravitational waves if they existed. But these, of course, are turned off initially. They are zero initially, because the universe was completely homogeneous and isotropic. So the space-time is described by that expression, but with phi and hij set to zero. Then you consider the possibility that there would be perturbations, and you also perturb the scalar field. So you consider the scalar field a part that depends on time, and another part that may depend on, that contains all the possible spatial dependence. That again is turned off initially, is set in a condition which is vanishing. So the background of the space-time is supposed to describe by this background, in which the two variables are the scale of the universe and the value of this scalar field. They are supposed to be in a condition in which the universe is expanding quickly and the field is rolling slowly down the potential. And then the perturbations, these possible space-time variations, are treated quantum mechanically. One elevates these classical variables and decides, now I'm going to treat them quantum mechanically. But in accordance to the previous standard, you start with them in the vacuum state. Okay? So the situation remains homogeneous and isotropic. And then you are told, but the situation, this state, this vacuum state, contains also fluctuations, quantum fluctuations, which is the place where people imagine something jumping around, which we saw is completely wrong. And from these quantum fluctuations, these quantum uncertainties are unjustifiably identified as if they were stochastic fluctuations, and those are the things that are supposed to give rise to the structure of the universe we have today. Now, if all there is described by the background space-time and the quantum state of the inflaton and all other fields which are supposed to be in the vacuum, the situation is completely homogeneous and isotropic. There is nothing in the dynamics to break the symmetry. How can you end up with a situation which is not symmetric? We say, with those elements, the answer is impossible. It's impossible to arrive at such situation. Of course, here we are facing again a misuse of the notion of fluctuation that, as we saw, is tied with the M problem, and therefore I think it should be impossible to address it without addressing the M problem. And we will then and then we will then face, how to say in English, face the music, yes. I don't know what you face, but okay. But okay, we face the music, so we have to take address some solution of the problem, for which we decided to take the spontaneous collapse approach. It contains clearly a means by which you could break the symmetry. This spontaneous collapse includes stochastic aspects that are actually able to break the symmetry of an initial situation that is not. I'm not saying that other approaches are not possible, but this is one where clearly it holds. For those of you that do not know the theory, there are various proposals for the theories, starting with the work of Girardi, Rimini-Weber, and Philip Pearl, and then there are some proposals for relativistic versions, and then some proposals to connect this with gravity. Okay, let me not get into the collection of those theories, but let me just present for you so you see an example and see that this is actual. You can actually write the theory. It's not a theory that you dream about. So the theory, it basically tells you that the system that has been prepared in an initial state evolves in time according to both rules. A rule that unifies the unitary evolution and the thing that we will call the measurement. So it contains the standard evolution controlled by the Hamiltonian in the quantum version. So this would be the Schrodinger, would satisfy the Schrodinger equation. If I take this part out, and this modification is the modification that involves this spontaneous collapse theory. It contains various features, the strength of this effect, the preferential basis or the operator to which the states are being driven by the collapse dynamics, and a stochastic function of time, and then you have a probability rule for the realization of a particular stochastic history of or stochastic variable, collection of stochastic variables as a function of time. Okay. This correction should be small enough not to affect high precision experiments in the lab that test quantum mechanics to very high levels, high precision levels, but should be large enough to ensure that the table is never found in a superposition of being here or there for more than a very, very small fraction of a second. And as I said, these theories can account for the breakdown of symmetries, and we consider them incorporating such theories into the inflationary cosmology. The theories have been designed to modify the space-time evolution of a quantum system, so we need space-time to be able to frame the theories. And that's another reason why we keep the treatment of space-time in classical terms. That, and also the fact that I don't really have a good theory to treat quantum mechanically space time. But as I said, we will use quantum field theory to describe all matter fields in principle. When one makes this statement, one is immediately faced with the fact that this semi-classical approach has been subject to a lot of criticism. In particular, there is an experiment, or a claim experiment, by these two persons which claim to have put a macroscopic object in a superposition, or try to put a macroscopic object in a superposition of being in two places and try to test the gravitational field of that. And okay, let's not get into the details because I don't think the experiment was really done as what they claim. But anyway, they nevertheless arrived at two conclusions which I don't dispute. The conclusions are, if the theory contains no collapses, then the field in the middle, the gravitational field in between the two massive objects would, according to the theory, imply that the needle doesn't move, and in their experiment it moves. I will not claim that this would not happen. So the theory would be inconsistent with the experiment. And if there are collapses, the theory is inconsistent because the theory would imply that, a collapse would imply that the energy momentum tensor is not conserved, while the right-hand side of Einstein's equations, which is what we will use, is automatically conserved. On the other hand, in a recent work with the team and another colleague, Elias Kohl, we analyzed the set of possible solutions, reasonable solutions to the M problem, and found that to be generic. So this problem appears there in basically any approach that you take to the problem. So it's not a problem of just choosing collapse theories, it's a problem that is going to appear whatever you do when you try to deal with the M problem in context in which you treat space-time as in classical terms. So again, we have to face the music here. So we'll face the music and say, well, this theory cannot be the fundamental theory, of how quantum and gravity are put together, but can be an effective theory, valid under certain circumstances and to a good sense of approximation. Just like hydrodynamics, nobody believes that, Navier-Stokes equations are a good fundamental description of a liquid. Nevertheless, we know that they are very useful and we use them and learn how to use them. Of course, breakdown of the theory will occur in hydrodynamics when the wave collides with the beach and foam forms and all sorts of things happen. And in this case, when collapses happen, the theory will, at that moment, not be valid. Okay, so how do you make a mathematically precise description of this setting? First, so please don't get scared by this. This is meant to just to say that we can define precisely what we mean semi-classical gravity is valid, and then there will be situations in which it is valid, and situations in which it's not associated with collapse, and we will glue the different situations in which it's valid, connecting the situations in which it's not valid. So the situation in which it's valid, we call it a self-consistent semi-classical approximation, and it consists of giving a space-time, giving a quantum field theory construction on that space-time, and giving a state of the quantum field theory in that setting, and then requiring that the whole thing is internally self-consistent, that is, that the curvature, the Einstein curvature of the given space-time is equal to the expectation value, okay, of the energy momentum tensor for that particular thing. This is the way to obtain something that you can equate to the classical left-hand side. Okay, I know a question the team will ask, but I will wait for it to happen at the appropriate time. Okay, the point of that story is that if you add to that a jump in the quantum state, the whole construction falls out, because the jump is going to imply that you change the energy momentum tensor, and therefore you need to change the space-time, and then you need to change the construction of your quantum field theory. So you cannot think as a jump simply as a spontaneous change of the state. It has to be a spontaneous change of one of these settings into a whole new setting. And for that, we need to devise rules of how you glue them, and we have studied them. Let me not get into too much of the details, but something very rigorous can be done. Of course, in applying it to cosmology, where I'm going to be dealing with a continuum amount of collapses or an infinite number of collapses, this becomes basically unmanageable. And we have then an effective way of treating them, which again is going to be using now Einstein semi-classical equations, and in this side, the energy momentum tensor of the inflaton. And the inflaton will going to contain two parts, both treated quantum mechanically, the part that doesn't depend on space, and the part that depends both on space and time. The background, again, basically reproduces the standard story. How am I doing on time? And then the parts that depend on space variables, we change variables. We go to the Fourier transform. This is just a detail, but these are treated quantum mechanically, and these are represented by wave functions that are centered at 0 and have a certain width. These are the famous quantum uncertainties, misnamed quantum fluctuations. But and as a result of that, by the way, the space-time variables that depend on space are also vanished, so the situation is homogeneous and isotropic. However, the collapse theory modifies the dynamics and then can change the state for the state of the inflaton field in such a way that the expectation values of these quantities now change. They are no longer 0. And we find them appearing, for example, in the semi-classical equation that you derive for this variable phi, the Newtonian potential, and appearing on the left-hand side, you have here the expectation value of the momentum conjugate. And you see here clearly that if this quantity was 0, as it was in the original vacuum state, the expectation value of this quantity is 0, then the metric variable would vanish, and you will have a spacetime that is homogeneous and isotropic. When the expectation value changes due to a collapse, then this quantity becomes no longer 0, and then this quantity becomes non-zero, and you have a real inhomogeneity or anisotropy in your spacetime. Okay, when you want to actually do it, you have to define what theory you are going to use. In this case, we use the CSL version of the theory adapted to the setting. Which are the collapse operators? You have to make a reasonable choice. We don't know why this is their choice. These are the choices that work, but with these particular choices, you reproduce a power spectrum, which is basically a characterization of how much variations, actual fluctuations you have at different scales in the cosmological setting, and we reproduce basically the standard result that is obtained by inflation, but now with the setting in which all the conceptual issues have been clarified. Okay, so you say, well, here you haven't really done anything but clean up the story by adding your collapse theory. I think I am very happy because now I can tell you a story. I can tell myself a story that makes sense. One of the interesting results is that if you assume certain values, certain characteristic, typical values for the quantities that describe the inflation field, you can read off out of the spectrum that we see in the CMB what is the value of this parameter lambda tilde, and it turns out to be of the order of magnitude suggested by the GRW people that designed this theory work in the experiment. Of course, if you make different choices and other people have done, you obtain different results, and this is a big debate that I'm not going to get into. But what I want to show you now is that even though for the scalar spectrum we obtain exactly the same, basically the same account as in the standard story, for the tensor spectrum, surprisingly, we find something dramatically different. And we find something dramatically different because we don't quantize the metric perturbations. That is, we don't quantize this Hij variable that was appearing in my metric. This is, however, connected through the semi-classical Einstein's equations to the energy momentum tensor of the scalar field. But in this case, and this is the thing that is treated quantum mechanically, this is the thing that is going to undergo collapses. But in contrast with the previous case, in this time, the quantity is quadratic in the object that is going to collapse. It's quadratic in the field that is going to undergo collapse. And that produces a dramatic reduction in comparison with the first case of. Okay, so here you see that for the tensor perturbations, we have a power spectrum that, well, it looks very similar but has important differences. The first thing is that it has a very different dependence on the length scale, the K variable. And second thing is that it's quadratic, precisely because it was quadratic in the field, on this quantity, which is a small quantity. It's called the inflaton potential in the appropriate unit. So here, for the scalar potential, the spectrum is proportional to this quantity. In the tensor modes, it's quadratic. So this produces a dramatic reduction, very different from the standard calculations in which the two things are basically of the same order of magnitude. So, for instance, here I have a graph in which we compare the predictions, the standard predictions of the tensor modes, the spectrum of the tensor modes. This is modes as a function of scale. Scale is measured in the sky in terms of angular momentum numbers, basically indicating the degree, the angle at which they become more prominent. And here is the magnitude of those. Here is the magnitude of those. So, size of the fluctuation, magnitude of the fluctuation. The red is the standard, the line obtained by standard analysis, and people have been very disappointed that they have not seen the famous tensor mode. There was a big deal a few years ago where people claimed to have discovered this tensor mode, and it turned out it was some type of noise. So inflationary cosmologists tend to be very disappointed at the fact that they have not seen them. And in our approach, we see that in the scales that people are looking at, it's simply impossible to see them by many, many orders of magnitude at the scales that they are. Okay, so I have a few minutes to go into the black hole information. 7 minutes to cover the black hole information story. Okay, as you know, Stephen Hawking discovered that quantum effects cause a black hole to radiate, and it should then lose mass. And the most natural thing to think is that as a result, it will disappear. Nobody has proved that, but it's a very natural expectation, leaving nothing but thermal radiation. On the other hand, you are often told that quantum theory requires a unitary relation between the final state and the initial state, but the state in quantum field theory is associated with the characterization of the fields on a Cauchy spacetime. And here, the first thing is that, while this thing that I call scry minus plus the point at minus infinity may be considered initial Cauchy hypersurface, the final one is not. So people often modify the demand requiring unitary relation between the states in scry plus and in scry minus, and this is unwarranted. There is no reason to believe that such thing would be required. It's not really required by quantum theory, but it's also very hard to account for. People have come up and collided with what they call firewalls, which are basically dramatic variations of general relativity in regimes you don't expect such variations to occur. So, to recast the black hole information problem in a setting that really there is a problem, you have to assume that quantum gravity somehow cures the singularity. There is no longer singularity. There is no longer that thing that prevented my spacetime from being, oh, well, I cannot reach. Yeah, there you see singularity. That's an end of spacetime and things that prevent you from having a Cauchy surface. If instead of that you have a diagram like this, in which the region that would be a singularity is a quantum gravity region containing at least a structure that allows you to define future and past and things like that, so you can put it in between. Then you can ask the question, if I look at the state here, how is it related in sigma 1, how is it related to a state later after the evaporation happened? So here, the black hole was starting to form, or if I start here, the black hole had not even formed, and you have an amount of matter collapsing to form a black hole, nothing in the outside, and at the end, you have just the Hawking radiation and nothing else. How can you account for this? And the answer is, you can't. You can't account for that if you assume that there is going to be a unitary relationship between the states in the two. But of course, we say, wait, quantum mechanics also involves lack of unitarity. When you make a measurement, there is lack of unitarity. But of course, nobody is going to tell you that there is somebody inside the black hole making measurements. Collapse theories, however, tell you that lack of unitarity is a property that is occurring all the time, spontaneously, in association with the collapses. So theories with spontaneous collapses involve non-unitary aspects in the evolution in general. We have studied this issue in several explicit papers. Let me quickly here go through. How much time do we have?
3 4 minutes.
Okay. So the point is, I can write for you the initial state, which is the vacuum in that part that I call scribe plus the matter pulse that is coming in. That state can be rewritten in terms of the state at in regions approaching the singularity. Sorry. In regions like sigma 3, I can write the state in that region sigma 3, and it can be written in terms of states that are characterized the fields in the external part of the black hole times things that are internal part of the black hole. This whole state is basically the result of unitary evolution of the state there before up to that hypersurface. And now we have to apply to this state the evolution in using CSL type theory, and we will assume that the parameter controlling the strength of the collapse, right, the lambda parameter, will not be a constant, but it will grow with curvature. So here we're inspired by Penrose and Dioschi, who like to tie collapse theories to gravity. We are going to say, we need that because we need, in the finite time that is a proper time that is available for the hypersurface to reach the would-be singularity, we need in that time to erase all the possible information that was inside the black hole. So making the collapse rate increase with curvature, we can increase the rate at which information is deleted by the collapse theory and actually delete all the information before you reach the would-be singular region. Okay, so this is the expression of what I write. So we start, in this story, I start with the initial state written in these two ways. The result of the collapse theory is to give me one of those states, have this quantum superposition of states. Collapse theory will produce one of them, will collapse into one of those states. This is no longer unitarily connected to the previous state. It's a pure state, nevertheless, but it's a pure state that is chosen with the stochastic variable, so I don't know which pure state it is. It's chosen with stochastic variable with a given probability. What I can do to describe things is sorry, and now I have to tell you what quantum gravity is supposed to do. It's supposed to cure the singularity and convert the state as it goes through the quantum gravity region into something that is a reasonable state at the end. So it will not affect the things that are in the exterior of the black hole, because that didn't go through the singularity, but everything that went through the singularity will become something that has to have almost zero energy, almost zero mass, almost zero everything. And the simplest assumption is that this thing we call the post-singularity vacuum. So quantum gravity effect is meant to, we assume it's to do this, to cure the singularity and to replace the state by a reasonable state. And then I can look at an ensemble of initial states prepared in this way and characterize now the ensemble of evolutions. And the ensemble of evolutions is going to produce for me final states that are going to be distributed over a collection of all the possible states. And one can see that the final state represents then this post-singularity vacuum, which is common to all the states, and the various states in the external part. But the various states in the external part combine to form a thermal density matrix, which is precisely what Hawking tells us we should see. So at the final state, I have, at the ensemble level, post-singularity vacuum and a thermal state, and I started from a pure set of initially identical states represented by a pure density matrix. So again, the picture is here. I had a pure state. I had this evolution, quantum gravity basically erased all the information that was here and lent it to something that represents the vacuum here. The Hawking radiation didn't go through that region. So it ends up at my final hypersurface, and I end up with thermal Hawking radiation at the end. And there is absolutely nothing paradoxical about the situation viewed in this context. Okay, so we think this is a very appealing story for dealing with the black hole information paradox, a paradox that has puzzled a lot of people for a while. We have found that this approach also seems to offer paths to address problems like the thermal inflation problem, which I didn't mention, and I didn't, of course, explain, and also the problem of time in canonical approaches to quantum gravity. There is much work to be done. We have done some, as I hope I have convinced you, but of course, in my view, we are probably at the beginning of the exploration, and we thank all the help we can get. Thank you very much.
Study this narrative of structure formation. Previously, there were enough details filled in, and you're filling in some of those details from that story, though it seems like it involves decoherence. So I was wondering if you could add in the details of decoherence in your story.
Okay. From my point of view, decoherence doesn't help you there. First of all, decoherence doesn't really help you in any situation to address the measurement problem. I think most people agree with that, because you explain with decoherence why certain interference, you will not see certain interferences if you do an experiment. But it doesn't explain to you why you have a definite outcome, and doesn't justify the interpretation of the elements of your diagonal matrix of the diagonal that characterize your decoherent density matrix. You are not allowed to interpret those as representing the actual possibilities of what will come out. That is an interpretational jump. So to start with, that doesn't work in general. But in cosmology, it becomes even worse, because in cosmology, we don't want to add any anthropic features to the explanation. Men and humans or any kind of cognitive being is meant to arise much later than structure in the universe. And the ways in which people try to use decoherence in this setting is to decide to ignore certain degrees of freedom they call the environment. You want to get decoherence, you have to separate your system into system of interest and environment. And the environment, the degrees of freedom that are called environment, are those that we cannot perceive. So the fact that we cannot perceive certain degrees of freedom tells me to trace over them. First problem, we. Second problem is now I trace over the degrees of freedom and, as usual, need to identify one of the terms that appear in the diagonal matrix as representing one realization. Each one of the realizations is going to be, could be inhomogeneous and isotropic, but the whole thing is certainly not. Actually, the density matrices that you obtain in this kind of situation, under some reasonable conditions, if, for instance, you don't meet conditions that imply that your symmetries don't mix environment with the other degrees of freedom, then you can prove that the density matrix you obtain is really proportional to the identity. And a density matrix that is proportional to the identity can be identified, will look like that in any orthogonal basis. So you will not be able to identify what are the possible outstates, even if you try. Did I answer your question?
I agree that it doesn't influence the interpretation of the measurement problem, but decoherence happens in the early universe, right?
What do you mean happens in the early universe? Happens is...
It's a dynamic.
Well, the coherence is a process, it's part of standard quantum mechanics, and it's a process that you can see happening as a result of your division of certain degrees of freedom that you want to look at and ignoring some degrees of freedom instead. So, are you telling me that something beyond ourselves is ignoring these degrees of freedom in the early universe? Or in what sense is happening? There is nothing happening. The only thing that happens is that the state evolves unitarily. The degrees of freedom are entangled. All the degrees of freedom are entangled. And of course, if you decide to trace over certain degrees of freedom, you will see that the reduced density matrix of your choice, of the degrees of freedom of your choice, has this feature which we call decoherence. But there is nothing physically occurring more than the interaction between the different degrees of freedom. Do you agree?
Thanks. Hi, Daniel.
Oh, hi.
Thanks very much for the talk. I have the clarificatory question about the zero post-singularity state.
Zero post-singularity, vacuum post-singularity state.
I mean, I didn't get if it's something that we postulate, if it's something that we expect the quantum gravity to get, and if this is the case, why? I mean, what should we expect of this very simple, very
This is an extremely fair question, and I should have emphasized. I don't know what the quantum theory of gravity is. Moreover, I claim that the people that work on quantum gravity approaches will also tell you that it's work in progress and they don't have a final workable theory. So I don't know what is that. But as I said, if you don't think that there are extremely large violations of conservation laws, which could be, but if you don't think that there are extremely large violations of conservation laws, and you realize that, by the time I have reached this hypersurface, most of the energy that was present in the initial state is in the form of Hawking radiation here, plus positive and negative energy contributions that come from here. That will lead to the singularity. And you think that quantum gravity cures the singularity, which was my explicit assumption. If quantum gravity doesn't cure the singularity, there is no black hole evaporation problem. So only under those conditions, there is a problem, and there is the problem required addressing. So if quantum gravity cures the singularity, As a result, it must produce here some reasonable state. And this reasonable state should be one that possesses no energy, because most of the energy was here. Almost no momentum on anything like that, because everything was here. It could be that there is a little remnant, that instead of producing, this post-vacuum singularity, it produces some remnant. Okay, that's a possibility. In that case, my final state will not be this simple state, but would be an entangled state, which outside looks thermal, and inside looks as, a density matrix for those remnants that have very little energy and very little momentum. For simplicity, I have assumed that there is one state that is vacuum, pure vacuum, and then the thing takes this form. The other solution is equally acceptable. Something that describes a density matrix of remnants that have very little energy, very little momentum, entangled with the thing outside, so that outside I have a thermal radiation. So that doesn't change the picture. It only makes it harder to write down. But yes, in this particular, I have made the simplifying assumption that after quantum gravity has cured, I obtain a state that, for simplicity, has zero energy, zero momentum. If you leave me a little energy and a little momentum, and you want to put remnants, the story will be basically the same. And of course, you will have in the final hypersurface something remaining there. This. Right. Yes.
Thank you. So when you talked about collapse theories, you mentioned this continuous spontaneous localization. And then in one of the solutions, you've mentioned the time ordering operator. So I was wondering whether you can say something about this, like what's the explicit form and how we should interpret the time ordering operator here.
Okay, so the time order operator is an operator that acts on the variables of the quantum operators and simply ensures that quantum operators that do not commute are placed in the time order according to the time direction. So if you have a product of an operator, this exponential will involve very many products of operators. In particular, this operator and this operator will appear in very, very large products. And since the integral there is over all times, sometimes the products will appear disordered. So you have to put them in the correct order. Of course, this version of the theory, as you see here, it assumes that the space-time and the time is given. When I have to deal with the collapse theory and construct the space-time, the problem becomes much harder than simply putting the time order operator, because now I have to make a whole construction of the quantum theory every time that I have a collapse, as you saw. And this, I said, becomes very, very difficult in practice, especially if you want to take the limit when the number of collapses goes to infinity. So we have done a shortcut and not done all that calculation in the story. But in principle, this should be a feature of whatever construction you do and whatever rules you do to, make up the space-time when you construct this out of the SSC constructions, right? Fortunately, when states are associated when operators in quantum field, ordinary quantum field, are associated with regions that are spaceless disconnected, so you don't have a time order operator, they commute. This is a fundamental aspect of quantum field theory. So you can expect that to be able to preserve that feature in beyond that and enforce it in the construction that we have. But we haven't done it.
Thank you. So can I ask about the way in which this sort of top to bottom approach, at the beginning you advertised it as the patches that you make perhaps pointing towards what might, pointing towards a fundamental theory, something like that.
Yeah.
And there seemed to be an interesting contrast between the two kind of case studies you gave. So in the inflation story, not only do you have a story you can make sense of, but it seems to have an interesting predictive aspect in the extent, to the extent, if you recover the scalar modes, then the prediction for the tensor modes is different to what other people had, and then you've got some interesting experimental stuff to look for. But in the black hole case, it's not clear. Okay, you've got some story that makes sense, but it's not clear how it's helping you sort of see what should come next.
Well, the point of the black hole story, in a sense, is that once you add collapse theories, and I noted that in order for my story to work, I had to do something to the collapse theory this time. I had to assume that the collapse rate becomes dependent. If not, if I don't make the collapse rate increase as I start approaching the singularity. Okay. So here is something in which I learn about what collapse a feature of what collapse theory is. Oh, he doesn't move now. What happened? Huh? Sorry, let me go to this. Okay. So here I have all the information. Here I have to get rid of all the information, no matter how much information was present. For that, I need to make sure, the collapse theory as it stands with a constant collapse rate is not going to be able to do that. And I have, find any observer, let me use the observer just for pedagogical reasons. Any observer that is falling towards the singularity will do so in a finite amount of proper time. We know what that is. So I have, in some sense, finite amount of time to get rid of all the information. If I don't have to be forced to tell you that quantum gravity is the one that is going to erase the information and pass the ball on into unknown things, I have to ensure that I erase all the information here. And for that, I need to make the collapse rate diverge as I go here. And for that, I need to make it dependent on the Weyl curvature, because here there is no Riemann curvature effect. Here I have both Riemann and Weyl curvature divergence. Here I don't have Riemann curvature, Ricci curvature. Okay, so it has to be the Weyl curvature. So here I learned something about what is the feature that I need to put into the collapse theory for it to do the job that I wanted. But I don't have any testable prediction like in the other case, which of course is more interesting.
I have a quick follow-up. So I still don't get what changes the rate. So if you take the standard CSI equation, so it depends on the mass of the different kinds of particles, right?
Right.
So I don't get what's going to.
So instead of putting the mass,
just assume
instead of putting lambda as a function of mass, normally it's lambda 0 times the mass, it's going to be lambda 0 times this. I don't probably pass too quickly. Here. So it's lambda 0 times something that is dependent on. So here you will have your mass dependence and everything. Here you will have something that depends on the Weyl curvature at the point in which the collapse is occurring. Right?
But you just assume it. So.
I'm just assuming. Yes, I said I have to assume something will increase the rate. Of course. I don't have the fundamental theory of collapse. I don't have the fundamental theory of quantum gravity.
But I mean, in the standard case, in the CSL case, that's a big assumption. Because again, I mean,
well, in the standard case, this quantity would be so small that would be relevant. You know, the Weyl curvature in the laboratory situations is extremely small, and this mass is meant to be something like the mass, the Planck mass. So this is completely, it's negligible. It's adding, you know, 1 with 19 digits after all. Or something like that. Zero, 19 digits after all. I don't know if I.
and very last point.
Yeah, but it's really the same point. But I just follow up. I mean, so think of these different GRW theories as different theories, and that they are all consistent with one another.
No, I think there are different theories. They all share features. I still need to choose the ones that best fit, that I can best patch together with gravity and quantum field theory. And I need to find a way to make them patch together. And I will have to wiggle with them, and perhaps with quantum theory, and or perhaps with, I mean, this is wiggling with quantum theory, but wiggle with quantum field theory and wiggle with the GR. Perhaps there will be corrections. So, yeah, I declare myself agnostic regarding many things. I know that certain things work, and I try to extend the range of working, but by changing some features, because I'm demanding more from the theory.
Let's end there.